In this lesson, we're going to look at trig ratios for any angle. Up until now, we've been looking at sine, cosine, tangent, and the reciprocal ratios in terms of only acute angles. So to look at this, we are still going to look first at an acute angle that's in standard position here, and we're looking at angle theta, where its initial arm is along the x-axis and its terminal arm is on point P, which has the coordinates x, y. We can think of what we can do is we can drop a vertical bar here from point P to the x-axis, meeting it at a right angle, and you see that now we have a right triangle on the plane where the distance here is x, our horizontal distance, our vertical distance is y, and we can call this distance r, which could represent the radius if you're thinking of an arc as a part of a circle that's being inscribed by this point as it rotates through angle theta, or you can think of it as the hypotenuse of the triangle. If we look at this triangle with respect to angle theta, we can see that y is the opposite. I'll just use a different color for that. That x is our adjacent, and that r is the hypotenuse. Okay, so if you think about sine as being opposite over hypotenuse, we can say then that the sine of theta is y over r. Likewise, cosine then will be x over r, and tangent, opposite over adjacent, will be y over x. And then our reciprocal ratios will be the reciprocals, so r over y, r over x, and x over y. Okay, so if you think of the trig ratios in terms of opposite over hypotenuse and so forth, we can replace our opposites and adjacents with this. And so this works for any point P in the first quadrant, because any point in the first quadrant we could make into a similar right triangle. We could find the values of x and y if we know the coordinates of point P, and find the length of r and come up with our trig ratios. So what we can do now is say, well, what happens if theta isn't an acute angle? So for instance, what if theta is an obtuse angle? So it ends perhaps in quadrant 2 instead. So what if theta is that kind of an angle? Or what if theta is a negative angle? So again, it starts here, but goes in this direction. Well, notice that in both of these cases, we can, from a point on the terminal arm, we could drop vertical to the x-axis, create a right triangle, and again, the lengths of the sides will be x, which in this case would be negative, y, and we could use an r again, and we could do the same if we have a point on the terminal arm of this angle, and again, we'll have a value of x, a value of y, and a value of r. And the thing to note is that the ratios that are on the previous section, the ratios are the same for all values of theta. So even if the angle is one that's more than 360 degrees or 2 pi radians, even if I were to rotate a couple of times around an end, if point P is on the terminal arm, we can say that the sine is y over r, the cosine is x over r, etc. Okay? The one thing to remember with those ratios is that when we divide, which is what we're doing with a ratio, our ratio is undefined if the denominator is equal to 0. So if you think about it, some of those ratios have x in the denominator. For instance, the tangent of theta and the cotangent of theta have x in the denominator. Okay, and so does the secant. Sorry, the tangent and the secant have x in the denominator. So which angles give us an x equal to 0? So if you think about it, if that's our xy plane, our Cartesian plane, x is equal to 0 along the y-axis, right? So if theta is 90 degrees, or pi over 2, or if theta is 270 degrees, or 3 pi over 2, we end up with x equaling 0, and so those ratios won't be defined there. So look back at the previous slide, and we can decide which ratios are undefined. So that would be when theta is equal to 90 degrees, or pi over 2 radians, or when theta is equal to 270 degrees, which is 3 pi over 2 radians. Okay, and so we can't have x in the denominator then. So x is in the denominator for the secant and for the tangent. Okay, so they are undefined for theta equal to 90 degrees or 270 degrees. Likewise, let's look at when y is equal to 0. Y is equal to 0 when our angle is 0 degrees or 360 degrees, or when we go halfway across and we're at 180 degrees. Okay, so that would be the angles are theta equals 0 degrees or 180 degrees, which is pi radians, or 360 degrees, 2 pi radians. Okay, then our y coordinate is 0, and let's take a look, when is y in the denominator? Y is in the denominator for cosecant of theta and for cotangent of theta. So they are undefined when theta is 0, 180 degrees, or 360 degrees. Okay? So let's take a look at a question using these skills. So we need to find the 6 trig ratios for theta if the point P, -2, -6 is on the terminal arm of angle theta. So if you think about the point -2, -6 is down here somewhere. Okay, so we'll call that point P. It's on the terminal arm. So there's our angle. So there's the initial arm. Okay, and we want to come up with the 6 trig ratios for that. So let's just put our vertical in here. So there's our x value, and x is -2. So we can say x equals -2. Our y value is -6. And we don't know the r value yet. Okay, so let's calculate that. Because it's a right triangle, we can use Pythagorean theorem. So r squared will be equal to -2 squared plus -6 squared. So r will be the square root of 40, which will be 2 root 10. Okay, and so now we can just pop our x's, our y's, and our r's into those 6 trig ratios. So the sine of theta, y over r, so that will be -6 over 2 root 10, 2 root 10. So let's divide top and bottom by 2 first, so we get -3 over root 10, and then we'll rationalize the denominator, so we get -3 root 10 over 10. The cosine of theta will be x over r, so that'll be -2 over 2 root 10. We'll divide top and bottom by 2, so we get -1 over root 10, and then we'll rationalize the denominator, so we get -root 10 over 10. And our tangent of theta will be y over x, so -6 over -2, which gives us +3. And we can do the same thing and find our reciprocal ratios. So our cosecant of theta will be -2 root 10 over 6, which will be, once we simplify that, negative root 10 over 3. Our secant of theta will be negative 2 root 10 over 2. Notice I'm just pulling the negative out front rather than just keeping it with the denominator. And that gives us negative root 10. And our cotangent will be our x over our y, so it will be 1/3. So notice that some of the trig ratios are positive and some of them are negative, which makes sense because as soon as we get outside of the first quadrant, either x or y, and sometimes both, are negative. So let's take a look at if we can figure out a pattern for when the trig ratios are positive. So in the first quadrant here, so in the upper right, x is always positive, y is always positive, and r is always positive. So any combination of x, y's, and r's are going to be all positive. So all of the trig ratios are positive here. In quadrant 2, x is negative, y is positive because we're still above the x-axis, r is positive, r is always positive. So if you think about the trig ratios, any of the ones that have an x with either a y or an r are going to be negative. So the only positive ones are the y over r and the r over y, which would be sine and cosecant. Okay, and all the rest of them will be negative. In the third quadrant, x is negative, y is negative, and r is positive. So here, x over r is negative, y over r is negative, and they're reciprocals. So the only ones that are positive are when we're doing x over y and y over x, where we've got a negative over a negative. So that gives us just tangent and cotangent are positive in this quadrant. In quadrant 4, our x's are positive, our y's are negative, and our r's are positive. So here it's just the x with the r that gives us positives, and that will be our cosine and our secant. So there's a little way to remember which ones are positive. It's possible to think it through each time, but there's a little mnemonic device that students learn. There's A for all, S for sine, and it's reciprocal, T for tan, and it's reciprocal, and C for cosine, and it's reciprocal. And one way to remember that, if we start at quadrant 1, would be all, or a smart trig class. So we've just created a mnemonic device using all, sine, tan, and cos. Others would call it the cast rule, but because we're starting in quadrant 4, maybe you want to call it a forecast. Okay, so come up with your own way of memorizing that. You do need to be able to say which trig ratios are positive in which quadrants. So here's another question. Given that the tan of theta is negative 3/4, so the tangent is negative, and the sine is greater than 0, so the sine is positive, find the missing trig ratios. If I gave you only that first piece of information about the tangent is negative in a couple of different quadrants. It's negative in quadrant 2, but it's also negative in quadrant 4. So we need to know that the sine is positive in order to narrow down which quadrant it's in. So since the sine is positive in quadrant 2, we know that theta has to be somewhere in quadrant 2, okay? And its tangent is negative 3/4. So tangent is negative. Tangent is also equal to y over x. In quadrant 2, y is positive because we're above the x-axis, and x is negative. So that negative actually has to go with the 4. So we can think of this as y equaling 3 and, x being negative 4. Okay, 3 over negative 4 gives us the negative 3/4 for tangent. Okay, so then let's calculate r. So r squared will be the sum of 3 squared plus negative 4 squared, which comes to 25, so r will be equal to 5. So now we can come up with the rest of the trig ratios. The sine of theta, y over r, so that'll be 3/5. The cosine of theta, x over r, will be negative 4/5. Makes sense. Cosine is negative in quadrant 2. The tangent of theta we already have been given. It's negative 3/4. Our cosecant of theta will be the reciprocal of the sine, so it's 5/3. Secant of theta will be negative 5/4. And the cotangent of theta will be the reciprocal of tangent, so it'll be negative 4/3. Okay, and that's it for this part of the lesson. The next part of the same lesson will be on the next video.